announce that we are hosting today a distinguished technical lecture from Professor Hassan. These lectures are once a year opportunities. We have distinguished technical lecture, distinguished executive lectures coming up in a month. You'll have also seen next month a couple of lectures, right? So these are not your usual seminar, so it's my great pleasure to introduce Professor Yasin Hassan, who is a Royce Weisenbaker Chair in Engineering and Professor in Department of Nuclear Engineering. And also Mike Walker, Department of Mechanical Engineering Professor, department at Texas A&M University. So he has a great experience and did very good work here in his career, which we'll look forward to hear some of them. But some of the highlights is that he worked for 7 years at Babcock & Lucas company in Lynchburg. And his research is focused on computational experimental thermohydraulics, reactor safety, laser-based flow visualization and diagnostic imaging techniques, system modeling, multi-phase flow, and advanced nuclear reactors. He's a fellow of American Association of Advancement of Science, fellow of American Nuclear Society, and fellow of American Society of Mechanical Engineers. His awards include 2008 American Nuclear Society Seaborg Medal, 2003 George Westinghouse Gold Medal, and 2004 Thermohydraulics Division Technical Achievement Award, as well as 2017 Landis Medal of American Society of Mechanical Engineers. He is a member of the National Academy of Engineering and a member of Academy of Medicine, Engineering, and Science of Texas. He was sworn in 2007 as part-time technical judge for Atomic Safety and Licensing Board panel of the US NRC. What is also important that he also serves as editor-in-chief of the Journal of Nuclear Engineering and Design, and also associate editor of Journal of Verification, Validation, and Certain Codification. Please welcome Professor Yasin.
Yeah. Thank you, Igor. It is really a great pleasure to be back here, and thank you for the invitation. As a matter of fact, 35 years, I don't know how many years, when I was at Babcock Wilcox Company, Mike invited me to give a seminar here when I was a young engineer. And it was completely different now. We didn't have microphone. And I remember maybe this, what they call it, transparency or whatever. And it was. Yeah, that's true. So it is a pleasure to be back. I always visit here every year. I'm on the advisory, and I see the change. It's really a lot of progress, and you guys are the new generation for nuclear reactor. So, I mean, we depend on you. We didn't build the last, I don't know how many years. I am very optimistic at the end to see that, and it was great. Also, what happened is I was, David Haller is one of my students, finished his PhD. He done a lot of nice work. He developed a lot of technique, measurement technique. And I was planning to present his seminar. Then I found out that he presented last week. So that's one thing. So please bear with me. I'm trying to come up selecting some of the work we're doing. At Texas A&M, my lab doing for the last 2 decades really is doing a measurement technique, try to understand the physics of I worked for 7 years, considered BNDW and running this code. I didn't understand. So that's really inspired me when I became a faculty member, is to zoom in, understand the phenomena in every experiment, and try to do that. So the last few years, I focus on the measurement techniques to come up with understanding the complex phenomena in a different component of nuclear reactors. So here I will try to explain some of the measurement. It's really, I will flash the things we did and what accomplished and that. So the last 2 years, we're focusing in getting high fidelity experimental data and then adding, trying to do a benchmark for that validation using the new tools of the computational fluid mechanics to be sure that you get the right result for the right reason, because I still believe that even using a high supercomputer, we have to understand, because there might be errors there. You might that sometimes I tell my student, yeah, you're using a supercomputer to get the wrong answer fast. So we have to look to the physics. I had a talk with Nam Dina. I learned from him. Nam Dina is my teacher, really. He's always come up with a new idea out of the box and so on to get that. So that's one of the things. So I will try to look at certain component of the reactor. That's also Kim Castle. You guys working on Castle. I worked a little bit. So I will look for different bundle of the reactor. So we have the new advanced reactor is liquid metal with a wire wrap. The bundle with a different spacers grid, and that's what Castle to reduce the crud depositions and so on. The gas-cooled reactor, you have a spherical bubble bed, also very interesting thermal hydraulic phenomena is very rich inside the core. So we try to study this phenomena in a different. So here, that work really is my student work, and so it is. So one of the things which really needed when we started before 3 Mile Island and after, we used the system code. It's 1D, so it was average quantity. You get the temperature or the pressure, but now for high efficiency and for high safety, you really need high spatial and temporal resolution. But to get these two, you can do it with CFD, you can do it with DNS, direct numerical simulation, or large AD simulation, or even on steady rads. But to get really this measurement, it's very hard, especially in a complex flow geometry like, as I mentioned, a spacer, a wire wrap, bubble bed reactor, and now micro reactor and molten salt. So there is a need of benchmark the transient and the steady state. Otherwise, we will be in trouble. So we have a lot of collaboration here and the partner. You can see we worked with some of the utilities, South Texas project, with some companies there. We try to solve some of the problem. It might be related is deposition of the debris from the containment on the screen that might prevent the water going back to the reactor. So that one, some work we did with South Texas project. We do also bubble bed and so on. We have some work with Belgium here, SCC, because they interested in liquid metal reactor. And we have a lot of work here, and plus Castle, which you guys are a major player here in Castle with Sandia and other labs. So that, this is stuff, again, stop here. Use that, my flow. So I am going to talk about some of the measurements here we're doing for preventing, and you are aware here with the crud deposition. So we doing some work, as I mentioned, in light water reactor, in advanced high gas cooled reactor. And for the validation, we have our own codes, but in the same time, we're using commercial code like Star CCM, Fluent, and the CFX. In addition, we have a lot of work with NIC 5000, which code we use it is for direct numerical simulations. Thank you. Direct numerical simulation and the OpenFOAM, which I see a lot of work here you're doing in that. I will skip that. Igor knows that more than me, and Namdina. What is the difference between verification, validation, and verification? And to solve is the mathematical equation correct, but it doesn't mean this equation really is right from the point of the physics. This equation doesn't reflect the real physics. So that's why the validation, you need experimental data. Here you need a good solution technique and so on. So V&V becoming a major task. Even American Society of Mechanical Engineering has a different committee, 10 for structure mechanics, 20 for fluid flow, 30 is for nuclear system. And now there is a lot of work scaling, and NAMDINA is collaborating in that one. So here is one experiment we'll try to do. And the reason there are interest here in North Carolina also is the spacer and the wire wrap. Wire wrap is used for liquid metal reactor, and instead of using the spacer grid, they have the rod and they put wire around it, and that to increase the heat transfer in the same time to reduce the vibration of the tube. So we need that. So there is a lot of CFD calculation, but the challenge here, how to validate it. So that's our work. So to do that, we came up with a certain scheme. Is our bundle here is 60 or number of that. Here is a spacer grid. So that work is done under also CASTLE. This is the data we get. It's running a star CCM with about 500 million nodes. It took about 2 months for the student to do that because it's a BlueJeans, I think it's a machine. But you can see the structure of the flow. So we're trying. Here is the most difficult is to use what kind of turbulence modeling. So that might be important to understand the phenomena so we can use other codes. But so to compare this data, we used certain rods has the same matching refractive index as water. So when you do that, it becoming transparent, and we use our laser technique to do that. So here, let's show some of the result is NUP, which ended, and that also before then we have with Stellar Power, because they are interested in liquid metal, and with Oregon National Lab because we use the NIC 5000 and so on. So that's the project. So the project is a bundle here, and we used this is wire wrap to produce rods. You can see the rods, and we produce this rods with acrylic. It took us a lot of time really to get the right pitch and to come up, develop a technique to wrap the wire on the rod. So, and then we put it and establish. So we have this kind of bundle here, and that it shows the bundle. You can see this is the rods. Then we have a certain fluid, we use it, and that fluid has a match it, so become a transparent. Then after that, we use our laser technique, which is presented in many papers. So you can use the two-dimensional and to get the velocity in a plane, or to use a stereoscopic. In this case, you need at least a 2-3 camera to get a 3D dimensional. So and that fluid is known that it has that. In the same time, we have particle image velocimetry, which you get a full field measurement here of the velocity, but also we like to validate it, so we use other technique, laser Doppler velocimetry at a local point inside the bundle. So this is kind of the first result, you get it inside the bundle. There is a lot of experiment performed in 1980s, 70 in Germany to get the pressure drop, but they don't know what is the structure of the flow here. So now we have all this stuff to do. That shows the experiment which we have, and the fluid and so on, and we use our technique and we do certain analysis here. But that shows, you can see here the velocity structure here at external of the sub-channel, here internal to get the average velocity, the wire here. So this is the velocity vector, you know, thousands of that, and in a transient way. So a lot of storage of data becoming like the data you producing from that. So you get the two-dimensional. But we like to see the exchange of the flow from one sub-channel to other. So we had to come up with a different way of measurement. So we get our laser here, our camera has to be on the top. So it was a lot of time, and we tried to focus in a certain several sub-channel here to get the velocity in the horizontal plane. And that shows some of our velocity here in the axial direction, 1, 2. And so you can see the reason here we use the two camera in that region and that. The reason of doing that, because we try to use high resolution, and that we reach it to length scale about 10 micron or 20 micron. So we're getting the fluctuation, we're getting to the smallest scale of the structure of the fluid. And we did that at a different Reynolds number. Here you can see 4,000 and 19,000. The flow comes in with this. The reason also, I forgot to say, we measure the pressure drop also. We have a sensor here, so we can get the pressure drop. There is a lot of measurement before is to measure the pressure drop, because that's one of the most important parameter for design this reactor. So we get that here, but also we get the time. You can see here, I don't want to bother you, you go in instantaneous velocity and so on with the time. So that's one of the things. But one of the interesting things came, the people in Belgium told me, sometimes you have a blockage in the channel. They find out in liquid metal, you get a blockage. They wanted to see what's going on. So we did block one of the channel here, so you can see block this two channel, and try to see what is the velocity below and after that. So this is becoming of interest, the people who building liquid metal reactors, is that you have the blockage and the different stuff. You can see the structure of the flow here. So we had a blockage at the center of the channel. We have a blockage in the boundary here in interior. So this data is very rich data for validation of the code. In Germany or in Belgium, they had another experiment, about 19 rods, here 61, and they sodium and they heat it. And it's interesting that they get only temperature measurement, and maybe pressure drop, but temperature measurement, and they did their CFD, no comparison. They could not know what's going on. So our data here, at least to get the physics phenomena, and so that some of interest. Again, this is just a flash. There has any experiment, you have to do uncertainty of. If you give experiment without this error analysis, no experiment, it doesn't. Like Igor mentioned, when I look at the paper coming in to nuclear engineering and the design, if the author doesn't have measurement, if he has a measurement only without any analysis, I return it back. Also for CFD, you have to do that. You have to do analysis or error analysis of your CFD, GSI, or whatever changes neutralization. So that's very important to get this, what's the percentage analysis of your experimental data and that. So I wanted to give this information because we like to have this as a benchmark. I think Maria liked to do that. So the data will evaluate it, and your experience with getting comparison between sub-channel code or CFD with high fidelity code. Here is what we did NIC 5000 as a code. So this is a comparison between NIC 5000, the solid line, and the data. So this is a code which ANL, the code Oregon National Lab. So they got our data and they did it with using large eddy simulation and compare that. It takes them a long time, like the experiment, really, I can say. This is, it shows the 3D, but it's not really clear. There is the exchange of momentum between sub-channel to the other. We should understand that and get. This one of the pressure measurements here, there is a lot of correlation of this measurement. So what we did our measurement from 2,000 to 20,000, you can see Reynolds number. So this is the data is, and we compared it with UCD, which is Chen Tadros correlation. Dr. Neil Tadros from MIT worked on that in 1980, and he just published a paper in NAD by refining his correlation for the pressure drop in the wire wrap. So that one of the things his correlation wasn't really, we done it. There is another figure, but it's not here, with other correlation, and you can see a large uncertainty there. But one of the points we are so proud of it, that we got at Reynolds number about 100 or 200, or 250. There is no any experiment for the wire wrap in a bundle lower than 2,000. It's amazing because, the reason is getting the flow rate. One of the most difficult things in the measurement is the low flow rate in the lab. It using ultrasonic or whatever it is. So that was the first point. We didn't find anything. So this correlation can be used, TerraPower using it for their design and so on. This showing the velocity in a wire wrap. The other thing we showed before is the bundle, is a mixing vane. You can see here also we used our fluid, came up, that's important to see the measurement in a micro scale measurement before and after. So that's very good for CFD measurement, is that you can average it and also get this measurement in, you can use it for other like Cobra, TF, and the sub-channel code. You can see how painful it is doing this 1 million vector here, and the time resolution 125 microseconds. So it's a huge, every time they want a storage also becoming experiment, producing a lot of storage. Maybe this data is important to machine learning, to train or to do that when we scale it or using it. So this data is available, and that. As I mentioned before, this is the reason I put this, Igor. We got a 3x3 from Dresden, and they ship it to us, a bundle. They have 3x3, and they want to do it measurement using our facility. Why? Because they have X-ray, And of course, they want to compare it. So the engineer came here, spending 6 months, put the experiment and that to get the velocity distribution in this. So we give them that, then take the data. When this sub-channel is about 1 meter and come, and it came to Houston, and our colleague German, he said a nuclear bundle. Then they took it in the custom and calling the president of Texas A&M, what's that? And so they called me, and I had to, it's the only channel, believe me, there is nothing there. It's a glass. And
they should have said it's 9-barrel gun, right?
yeah, that's, so then we had to send the student down to pick it up and sending a paper that it is, oh my gosh, what a mess. So you can see. So next time when I ship something, I don't write. But here to show, you have to have error. If you don't have this error parts, forget it. This paper will not publish. So please, when you do analysis in the lab, you have to do that. Here also to show some of the work, we did it here to show you, see, you have a spacer 5x5, we got it from Westinghouse, and we put the fluid here. This is a new fluid, has matched refractive index as the glass. Here is some of the air. Then it's really beautiful. You can use a laser, you can do that. So we did a flow visualization. You can see the uncertainty. A colleague from Brazil, he came and spent the time because he has funding to do it. We don't have funding because the Department of Energy rejected my proposal, but I didn't care. So I went ahead and did experiment. There are about 2-3 students working on that for PhD. Some of them Oak Ridge National Lab, others went to other places and so on. The guy who did CFD here, after he did CFD, he's from Italy. Luigi. Then after that, now, do you know what? He has his own financial company in Europe using machine learning. And he's happy, I don't want. So you are a what you're learning here is not in nuclear engineering only. You can work on any place, mechanical engineering. My student work in petroleum, pharmaceutical company, because you do 2-phase flow, so powder. So one of my students, even at 1990, he couldn't find a job. So he finally found a job in Virginia in a pharmaceutical company. So I saw him one time at the airport. I said, oh, Mark, you should come back to nuclear, it's coming back. He said, Dr. Hassan, are you crazy? I am going to Switzerland skiing. If I'm nuclear engineering, I wouldn't go there. So what happened is, you guys, you're going to build a reactor, build everything, you will send us to the moon. And maybe beyond the moon. As a matter of fact, in NASA, there is a program they trying to, so there will be a lot of work in fluid mechanics, in other areas. So what you learn is this tool, be careful. This can be used in any other application. For the sake of time, this is a comparison between, I believe, maybe CFD and the data here. Anyway, so this data is very rich, we can see. But this is the mixing, very close to the mixing. There is no result like that to get it close to the mixing vein. But we trying to do that, as you saw, when we run it with 1.5 billion node, it took me 3 months. The student couldn't graduate. He was waiting for a result. He goes to the bar drinking all night, and then come the morning, computer is not giving a result. So he's ended up with, it's really bad. So here what we try to do, I'm sorry, that's what I wanted to get. This is a steady, we used RANs, or something, I'm doing something wrong here. But I have to go back, I'm sorry. Okay. Please, I'm going back. Yeah, I want to show you that. What we used here is rands, and you can see rands is doesn't show any fluctuation we have, right? Is a symbol here. There is no any fluctuation. Oh, I'm sorry. Oh. Any fluctuation, because even so here there is no resolve it. So we're using here K omega, okay, in a steady. Then what happened? We have a large eddy simulation. So we, instead of averaging average of Navier-Stokes equation, Reynolds average Navier, this is a partially average. What happened is there is f fraction is to get sum of your Reynolds number through k epsilon or so on, and the other part is resolve it. So what we do, we change this f here is 0. That means we don't resolve anything. We use the like you use k omega. And you can see there is nothing showing some of that, but there is no. But once you have, you have here, add some of that f, you can see at 20% to resolve it, you get some fluctuation. At 40%, large eddy simulation, you get better fluctuation. So what we can do is using that to get, if I need all more detailed resolution, I can resolve it here and then forget about that in this. So there is a factor F I was talking to Nam, maybe with his machine learning to get the best values at, and it can be changed from one location. You need here better result, so I can use here 90%. Here I can use 0 because I don't care. Here is I know the structure of the velocity. So that's the new thing is we trying to learn about it, to understand using our data, because our data, I believe my data, but always the experimental guy doesn't believe his data, but the person who does CFD, they believe their data, which is always wrong, by the way. So I think that give you, also you can hear about bubble bed or gas-cooled reactor like X energy. So we done some experimental. Also we play with our fluid here. You get the sphere randomly and try to get the data here to give it to the people to do CFD. And they do, we give them even the structure, the frame, everything, and then they do their CFD. It doesn't match with our experiments, so they come and they tell me your experiment is wrong. And we tried not to tell them that. So we're working with very closely with the CFD to get the structure of the flow between the spheres, maybe doing average or machine learning when you do instantaneous. So that helped the new design of the reactor. You can see here several spheres. What a mass is that flow, recirculation, some area. So you may get one area here, unlucky sphere comes here, we get hot spot because there is no dissipation of the heat. So you will end up with a problem. Also, again, remind you, you have to do uncertainty. So that's what we're doing, and some of our students getting this data to do some simulation of it. And I go back one. Okay. Oh, yeah, here, what happened is our friends of CFD, they said, you don't give us this random calculation. So we use the scheme here is a kind of tomography to construct the sphere. We give them the right calculation of the sphere. So that shows some of the ways we do it. You see the sheet of light going up, so we get exactly the CAD design of the sphere, and we give it to them, and then they do CFD. So they come back and they don't. Also, they tell me they need the right inlet conditions, so we give them a full field velocity here, inlet conditions. So we're trying to reduce their excuses of getting a wrong result. So I work hard on that to prove their code is wrong. Okay, so that's why. That's why Department of Energy don't like me. So I submitted that proposal, NAM, and always is they didn't like it. So one of our students put several sphere to get the flow between the sphere, and he used also NEC 5000 here. Elias showed that. And he presented that in the flow visualization, fluid engineering division, and he was happy he got the first award. His name Lambert, and he works in Kairos right now. So he did that, but he worked with other code. So that gives you some idea what we are doing in our lab. How I'm doing on time. Oh, still I have time? Oh my God. Yeah, I think one of the things we did, I don't know if I have it here. I want to go to this one. I remember. I told you when you have certain sphere, you may get a recirculation, and that's my expectation here. So maybe this point to get too hot. So what will happen is you get a recirculation. This is experimental data to prove that we have a dead zone here. And what will happen, this is from seed ball. He got it showing the picture of one sphere in KFA in Germany, shows the oxidation. All the sphere is so clean except this unlucky sphere got stuck, and it happened on this, I call it dead zone, and it damaged. So they wanted to know how this sphere, not the other. It got in a certain pattern, got a lot of recirculation, got hot spot you can see. So this is a real sphere. He gave it to me, seed ball, in 2006. He got this picture. He retired now from Oak Ridge. By the way, he has a good program in his garage. I'm trying to get it at home. He knows how to get this spots with a very simple correlation and that. So I think that give you idea what we're really trying to do with collaboration with you guys giving all of that. So that give you some idea. I don't know if I have one movie, if you have it. I like movie. I tell my student, you can ask David Holler. He couldn't graduate until give me a nice movie. Right? I tell them that's what, because that helped me to understand the things a little bit. So
I have the same criteria in my group.
yeah, yeah, that shows some of our work. I don't know. Yeah, our lab, but I think I give you everything here, maybe what I have. I thought I have a movie to show. Yeah, this is done by you guys in subcooled reactor, in subcooled cooling and so on. Okay, it seems I don't see it, but it is experiment we conducted for NEA, is mixing in the cold lake of the reactor. So it seems I don't have it right now, but I will be happy to answer any question. In the same time, if I find it, I will send. Thank you. And,
Let's think about it, Hassan.
yeah, thank you.
And it's indeed good time for questions.
I have a very quick one to see. What is the reason for using K omega over K epsilon? Is it because of the boundary and avoiding?
Yeah, I think there are a lot of different models of turbulence, and every like K omega can help when you have a recirculation. K epsilon is not. Like you remind me, maybe Gur heard it. I was in mechanical engineering, and as a student, I am on his committee. So I slept during the presentation. So I got up and I heard he doing turbulence K epsilon. So I said, did you use any other model like K omega? Because I see your turbine, there is a recirculation. So what he was answer is, what his answer? I said, that doesn't make any physics. He said, yeah, when I run co-omega and the other model, the code didn't converge. That's not an excuse that the code didn't converge. So I said, okay, thank you, I left. That. So, in other words, we have to understand when the people develop K-epsilon, why they did that. I think that's a simple model. And then you have K omega, you have large AD, you have other ends. Understand when to use that model. Right now, doesn't agree with me all the time, by the way. Yeah. Right. Yeah, so that's important to, yes.
Just to follow up with the same question, for this particular flow scenario, isn't a nonlinear anti viscosity
Yeah.
more appropriate?
Yeah, nonlinear. So you have to use nonlinearity in the turbulence model.
Yes.
Is that what you're looking at?
Yes.
That's true. Even in the mixing vein, we find also you have. That's why a lot of our colleagues, right, producing this kind of model. But that's why I'm trying to come up with this partial. This code, this bands, partial average Naviers, is not my model. They used it in aerospace. Germagi, and used it a lot. So I thought, wow, this model makes sense. Let's do it. So it's not mine, but we published 3-5 paper on that. So it is good to get the stuff from other discipline to do it. You don't have to be in the box. That's what Namdina told me. I have to think out of box, right? Okay. Any other question? Would be yes.
Yeah, you showed some really great high resolution and spatial and temporal data. And I was wondering how you'd go about using that data to validate a DNS code without too much averaging.
Yeah, we can. We can. One of the things I think in the wire wrap, they run DNS, direct numerical simulation. So after that, we convert the mean velocity, the fluctuation. There is a lot of other things to see.
Can you look at instantaneous, like eddy size?
Yes. Yeah. We have some of the work. We looking for proper signal decomposition, POD, from the experiment and also from the calculation. And it's really amazing how, so we look into different eigenvalue, different scaling. Like I said, we can reach very close to Karamagov. So also we done is the spectra. So you have your spectra analysis from your CFD, especially non-transient, but we have the data also. We have that in a twin jet, and it is a benchmark, so you can. So in other words, yeah, it's getting there to do it. But again, it's a very simple experiment. You know, the model like 2 twin jets and all of that is very simple domain because you have to use a very high resolution camera. And that's why I used the 2-3 camera above each other to get a larger domain, because the pixel has some people using one camera for a large domain. So what is the resolution is 1 millimeter, 2 millimeter, and your micro scale is less than that. So you can have to balance that. Also, because the camera is very expensive, you know, $100,000 if you get a high resolution camera with large that. So we get that not through nuclear engineering anyway. We had a project NIH, and one of the colleagues is in chemical engineering doing bio and that for DNA. So he wanted high resolution, so he put 500K in NIH. Then they gave him the camera, so I got it, I put it in my lab, and I'm using it. Not any, NUB would not get this infrastructure. So it's really from other sources. Yeah, that's a good question. Yeah. Yes.
Maybe I can ask first. Yeah. So I'm actually wondering what will be the pretty new progress onto the near wall measurement, because like 2 years ago when I attended a conference, I tried to find some validation resource for my interfacial force study on the wall force, and then find out PIV has actually a large arrow near wall. So I'm not sure during the recent 2 years if there any progress which would help us realize people.
Every scheme or every technique has advantage, disadvantage. You are right. PIV, particle image velocimetry, close to the wall will get you an error. Because what happened, we find out the seed, you have to put a tracers. And this tracer is about 1 to 3 micron. And it's unfortunate, it doesn't want to go through the wall. So there are some tricks we do. Close to the subcooled boiling, we inject the tracer to get. Also, we don't use PIV, we use something else, it's called the particle. So we trace every particle. Also, when heated surface, what happened, you're changing the refractive index. So if you have a seed here, it will be moved in the camera. So you have to do a lot of correction. In other words, we succeeded to get it in a certain application close to the wall. We did that for subcooled boiling. And my student spent 10 years on that until he finished. Carlos, do you remember? Yeah, he liked to do that, so he stayed 10 years. I tried at the end, I kicked him out, you know. I said, no money, nothing. But it takes time, but you are right. Yeah, PIV is not, you have to be careful.
DNS to be rescue, right?
Yeah.
We'll figure it out.
Yeah, right. DNS can do it. If you, yeah, maybe. Yeah.
You showed some very interesting flow schemes around blockages.
Yes.
And you mentioned that it is of specific interest in metal-cooled reactors. I was wondering if you can elaborate on that and why it's what kind of blockages and why is it of interest in metal-cooled reactors?
For liquid metal reactor, there is a blockage. Is that right, your question? What happened, they tell me in Germany, they found in liquid metal sodium that you get deposition. It is like the CRUD in light water reactor. You get the CRUD. So they found in a certain area, especially with the wire wrap, you get area blockage. And so the flow cannot. And we, in our experiment, I used solid blockage. Do you know what they're telling me, Catherine? This blockage might be, you should be as a porous media. The flow will go through it, but not complete, like 50%, like a void fraction and that. So it's a porosity. So it's interesting. We tried to get maybe a small piece and make a hole in it, so I know the void that. So that's from the chemistry or something. I'm not really, but they told me this blockage, they very interested in it for liquid, because they building a liquid metal facility in SEK, and that one of the, we may have this problem, by the way, in VTR, if we're going to build it, right? Yeah, he working on it to get building VTR. He needs a, yeah, that's right. So you can get any deposit of that. It needs $7 billion to build a VTR facility. So we'll see. That's okay. Okay. Oh, okay.
question is that for these methods that you presented for
transparent,
Yes,
but liquid metals are not transparent.
yeah.
It's like you generate high fidelity data obtained for water, and how to like scale this data for metals.
Yeah, yeah, that's a good question. What we're doing is, this is the talk to Maria about that. This result for the friction or Reynolds, the pressure drop. It's a function of Reynolds number. So what we do in this case is isothermal. So it doesn't matter if it's sodium, lead, water. We did it with different, even with air to get. So it's a function of Reynolds number which has the property. So, but if you're going to heat it, you have to look to other scheme. That's it. And the other scheme, we think about it, I have it here, but I'm worried. We have X-ray, so non-intrusive stuff. So that will get you some velocity. We use that in the bundle now with a bubble coming in and trying to introduce that to get some information. So the other scheme should be something else, okay? Non-intrusive scheme. And there are some methods to do that. One of it is X-ray and ultrasonic. You can use that. So you can use any liquid inside. Sodium, high temperature, hostile environment because you measure from out. So that's a good, this is a very good one. I think there are a lot of requests of proposal for that, like APRA, E, and so. The instrumentation is important. So it has limitation. Nothing can work for one size fits all. No, yeah. Okay. Any other question?
Maybe one more question, anyone?
Yeah, I have a movie, but I don't know. Next time I would show it to you.
One of these, so yeah.
Yeah.
Something for you
Okay.
to recognize you.
Okay.
So-
Thank you, sir. Yeah. Thank you. Yeah, that's great. Thank you. Oh,
Small present.
okay.
It's fragile.
Thank you.
Very
Very good.
interesting.
Yeah.
Thank you.
Exactly. I will not write here any nuclear related. Otherwise, I will not go through X-ray. You know.
We need to take a picture.
Okay. With these two here. Okay. Yeah. Thank you.
Let's take Professor Islam.
Thank you.